Okay, let's dive into this explainer and take a look at how massive new infrastructure updates from Google and NVIDIA are solving what is easily one of tech's biggest headaches right now, the staggering operational cost of AI inference. If you've been tracking the AI space, you already know that building these models is really only half the battle. Actually running them efficiently at scale? Well, that's where the real challenge lies. So today we're unpacking exactly how this new hardware and software co-design is completely changing the game. We've got a packed roadmap today. We'll start with the AI inference bottleneck, move right into scaling infrastructure for less, and then securing sensitive data. After that, we're covering automating startup workloads, simulating manufacturing, and finally, ecosystem impact. So this is literally the multi-million-dollar question. Because while models are getting smarter, faster, and way more capable, the sheer computational cost to actually run them is creating a massive bottleneck for real-world business adoption. Think about it. If inference costs outpace the actual value the AI generates, the whole system just stalls out. Let's start with Section 1, the AI inference bottleneck, looking at the baseline problem of scale and cost that enterprises are facing today. Now, the sheer leap in efficiency here is absolutely staggering. By utilizing a highly integrated hardware and software co-design, Google and NVIDIA are fundamentally altering the math of AI operations. I mean, we aren't just talking about a modest 10% improvement here. This new architecture delivers up to 10 times lower inference cost per token compared to previous generations, all while achieving 10 times higher token throughput per megawatt. So for a business doing large-scale AI processing, you are serving 10 times the volume for the exact same power footprint. That is a game changer. So how exactly do we achieve that? That brings us to Section 2, scaling infrastructure for less. Let's see how this efficiency happens physically. To understand this massive drop in cost per token, we really need to look under the hood at the bare metal infrastructure. The raw muscle here comes from Google's new A5X server instances, which are running on NVIDIA's Vera Rubin NVL72 rack scale systems. But raw power isn't enough. Having immense processing power requires a highly efficient traffic controller to prevent bottlenecks. If data can't reach the processors fast enough, well, that incredibly expensive hardware just sits there idling. And that is exactly where the networking solution comes in. Connecting thousands of processors requires massive bandwidth to prevent those processing delays. Think of standard networking kind of like a congested city street. To fix this, they've paired NVIDIA ConnectX-9 SuperNICs with Google Virgo networking technology. You can think of this new setup like a massive, highly optimized superhighway system. It routes data perfectly, ensuring your GPUs are continuously fed with information. And that means you aren't wasting a single cent on idle compute time. Just to put this into perspective, 960,000. That's the jaw-dropping scale we are talking about here. With this networking configuration, a single-site cluster scales to 80,000 GPUs. But it gets even bigger. A single multi-site deployment can now perfectly synchronize up to 960,000 parallel GPUs. Routing data across nearly 1 million parallel processors demands absolute precision, and this integrated network is designed to handle that exact challenge effortlessly. The absolutely crucial takeaway here is that this isn't just about throwing faster chips at a problem. Mark Lohmeyer over at Google Cloud really hit the nail on the head. It's a truly integrated, AI-optimized stack. They are giving customers the flexibility to train, tune, and serve everything, from frontier open models all the way to complex physical AI workloads, completely optimizing both performance and cost across the board. But let's be real. Raw compute power means nothing to regulated industries like finance or healthcare if the data isn't secure. So let's move to Section 3, securing sensitive data. Historically, highly regulated sectors have stalled their machine learning initiatives purely because of data sovereignty concerns. They simply couldn't risk exposing proprietary data. Enter NVIDIA Confidential Computing. This is a hardware-level security protocol ensuring that training models operate within a heavily protected environment where prompts and fine-tuning data remain completely encrypted. It quite literally prevents anyone, even the cloud infrastructure operators themselves, from viewing or altering your underlying data. Let's look at how this builds in practice. For highly controlled environments, Google Gemini models running on NVIDIA Blackwell GPUs are entering preview on Google Distributed Cloud. That means you can keep frontier models entirely within your own walls, right alongside your sensitive data. And for multi-tenant public cloud users, they're introducing confidential G4 virtual machines equipped with RTX Pro 6000 GPUs. So you're bringing those exact same cryptographic protections to the public cloud, eliminating massive compliance overhead for those regulated industries. All right, from the massive enterprise, let's transition down to the startup garage. Section 4, automating startup workloads and accelerating agility for early-stage founders. We all know that building multi-step agentic systems is incredibly difficult. You have to connect large language models to complex APIs, you're maintaining continuous vector database synchronization, and you're actively mitigating algorithmic hallucinations. Startups have historically bled a ton of cash trying to manually manage these complex agentic training loops. It's a massive headache. But by using managed training clusters on the Gemini Enterprise Agent platform, which is powered by tools like NVIDIA NeMo for reinforcement learning, all that heavy infrastructure management is fully automated. It handles cluster sizing, failure recovery, and job execution for you. Agile teams can finally focus entirely on model quality instead of server crashes. For example, a company like CrowdStrike uses these exact clusters to generate synthetic cybersecurity data, heavily accelerating their threat detection without getting bogged down in low-level server management. And this flexible provisioning directly optimizes costs. While large enterprises might scale using full rack-scale systems, startups can leverage highly affordable, fractional virtual machines. We are talking about provisioning just 1/8 of a GPU. This is huge for the ecosystem. It gives you a cheap, fractional compute option that fully supports rapid prototyping, testing, and iteration for founders who are, constantly watching their burn rate. Let's step out of the software startup world and onto the factory floor. Section 5, simulating real-world manufacturing. Heavy industry relies on decades-old legacy systems, which makes applying AI incredibly tricky. But this simulation pipeline, it's an absolute game changer. It's like a 3-step magic trick. Step 1, developers bypass the usual translation issues of legacy CAD data using NVIDIA Omniverse. Step 2, they construct physically accurate digital twins and train robotics in the open-source Isaac Sim framework. And Step 3, they deploy those successfully tested workflows. Simulating workflows in a digital twin before real-world deployment prevents incredibly expensive manufacturing mistakes. Furthermore, by deploying specialized AI microservices like the Cosmos Reason 2 model onto Google's cloud infrastructure, vision-based agents and robots can seamlessly interpret and navigate their physical surroundings. Developers can literally jump straight from computer-aided design to living, breathing industrial digital twins that continuously optimize actual factory performance. It's wild. Finally, let's wrap things up with Section 6, ecosystem impact and returns. Let's see the quantifiable financial returns early adopters are actually seeing in the real world. Snap is a perfect real-world example of how scaling this infrastructure drastically cuts everyday operational costs per token. By transitioning their data pipelines to GPU-accelerated Spark on Google Cloud, they have massively reduced the extensive costs typically associated with large-scale A/B testing. And Schrödinger shows us that time is literally money. Over in the pharmaceutical sector, they are leveraging this accelerated computing architecture to compress highly complex drug discovery simulations that used to take weeks into a matter of mere hours. Turning weeks of expensive pharmaceutical compute into hours is just a massive financial and operational victory. The ecosystem scaling these tools has expanded brilliantly. It's spreading like wildfire. Over 90,000 developers joined this community in just a year. Startups like CodeRabbit and Factory are already applying NVIDIA Nemutron-based models to run autonomous software agents. And companies like Able, Mantis AI, Photoroom, and Base10 are building powerful generative solutions on this exact stack. It is proving without a doubt that this co-designed hardware acts as the perfect, affordable launchpad for autonomous agents. As we wrap up this explainer, the rapidly falling cost of AI inference really opens a fascinating door. The barriers to scale are completely crumbling thanks to integrated hardware, networking, fractional compute options, and highly secure environments. So, if computing power and cost are no longer the bottleneck, what physical systems will we automate next? That's the million-dollar question you should be watching in the months ahead. Thanks so much for joining me on this deep dive.